Hello and welcome to our webinar on multi-signal fiber technology. Today we're going to talk about the savings that can be achieved by sending multiple signals through a single fiber core. First, we're going to share independent research sponsored by Communications Specialties, Inc. that shows the kinds of television signals being transported through fiber. Second, we will make the economic case for sending multiple signals through a single fiber core. And finally, we'll share the technical information needed to implement a multi-signal fiber solution. I'm Josh Gordon, a broadcast industry consultant whose firm did the research, and I'll also be host of this broadcast. Our technical speaker today is John Lopinto. John is an engineer's engineer. Before starting his own company, he held senior-level engineering management positions at CBS, HBO, and at Time Inc.'s Video Information Services division. For the past 17 years, he's led the technical product development of fiber products at Communications Specialties. Throughout the broadcast here, we're going to ask you for questions. If you look at the screen, in the lower right-hand corner, there's an area where you can type in your questions. We'd love to hear any questions you have and encourage you to ask them. So let's get on with the show. First, let's start with some research that kind of frames the conversation that we'll be having today. We'll use the findings from CSI's industry study on fiber use. This study surveyed fiber use among television and professional AV users. As we can see, this one talks about the different kinds of signals being transmitted at different facilities. So we can see here that of all the different kinds of signals being transported, SDI and Ethernet led in frequency of use, with computer video as third. Now on the next slide, we can see we asked the same audience, the same level of options, and we asked which of these different kinds of signals are being combined through a single fiber core. And we can see that SDI and Ethernet are still the leading options. But in this case, data moved up to the second place. Now, on the third slide, we can sort of see this is where we asked, okay, do your clients transmit more than one signal of information? So here we're asking if they're combining different signals down a single core of fiber, and we can see that about a third said no, each signal gets its own single core of fiber. So this can be a real opportunity to save money and increase efficiencies. And now John Lopinto will make the economic case as to why this is an opportunity for improvement. John?
Thanks, Josh, and welcome everyone. How you doing today? Again, remind you to ask any questions. We'll try to integrate them as we go along, and if not, we'll get to them hopefully at the end. But we'd like to thank you ourselves here at CSI, as well as the folks at Camplex for welcoming us. Okay, let's talk a little bit about the economics of fiber. And the first thing I want to do is compare it to coax. One of the misconceptions out there is that a given length of a single core of fiber costs more than or about the same as that of coax. Well, as you can see from the first point on this slide, a single core fiber, about 3 millimeters in diameter, PVC jacketed, is about 19 cents a foot at retail. The prices vary widely depending upon whether it's wholesale, how much you buy, but in bulk, unterminated, it's about 19 cents a foot. Now compare this to 1694A coax, which is commonly used today for SD-SDI, and which is more than 3 times the cost. Now, what does this mean economically? Well, on just one fiber, one single core of fiber, we can communicate bidirectionally. We can send multiple baseband signals on that one fiber, and we can send multiple wavelengths. And we're going to talk about how we bring all this together in the slides that follow. But the results are lower installation costs and lower operating costs as time goes on, and of course that means more lower maintenance as well. It's just mechanically there's less to it, a fiber optic installation compared to coax.
Now we're going to talk through the technical side of implementing a multi-signal fiber solution. As you begin a new fiber application, there are several technical issues to consider. First off, there's two kinds of fiber that need to be understood, single mode and multi-mode. John will explain the distinct differences between these two. John?
Okay, well, let's talk a little bit about the basics. As Josh mentioned, we have single-mode fiber, we have multi-mode fiber, and one misconception I want to dispel right off the bat is that if you want to transmit multiple baseband signals onto a fiber, the misconception is that you must use multi-mode fiber. There's a perception that the multi and multi-mode corresponds to multi and multiple signals, and that's not the case. And we will show you the difference between multi-mode and single-mode fiber shortly. The other thing about the basics of fiber is that there are common wavelengths that are used. And these wavelengths are the not so much the colors, because these are invisible, but the different wavelengths that correspond to the different wavelengths that we use to carry the information. 850 nanometers is commonly used for multi-mode fiber. It's commonly used for multi-mode fiber, and it's used primarily for short distances. For longer distances over multi-mode fiber, we increase the wavelength up to 1300 nanometers. 1310 nanometers and 1550 are the typical wavelengths that are used with typically used with single mode fiber. The longer wavelengths of 1550 nanometer allow us to go longer distances because there's less attenuation in the fiber itself. Now, inside of the fiber, between multi-mode and single-mode fiber, the core, the actual part of the glass where the fiber travels in multi-mode fiber is a lot wider in diameter than it is for single-mode. But what happens is when we launch the light into the one end of the multi-mode fiber, the light disperses and it bounces off of the sides, so that when it comes out the other end of the fiber, the wavelength, the modes, the different beams of light do not all arrive at the same time, and we call this dispersion. Also, the intensity of the light, or the brightness of the light, the power of the light, is also attenuated a great deal. It's the analogy that I like to make is if you had a handful of rubber balls and you threw them into the end of a sewer pipe, hoping that to get them out the other end. Well, what would happen is those balls would disperse as soon as you left your hand, and they would bounce off the sides of the inside of the sewer pipe, and by the time they got to the end, they'd lose a lot of their velocity, a lot of their speed, and they would not all come out at the same time. And this is very analogous to how light travels inside of multi-mode fiber. Inside a single-mode fiber, however, the light tends to travel in a straight line. It's a single beam or single mode of light, and the result is that it undergoes far less distortion and far less dispersion than it would inside of multi-mode fiber. And this gives it its high bandwidth capacity, if you will, compared to multi-mode fiber. Now, the different fiber cable types that there are. Let's talk about multi-mode fiber specifically. Its core size, that is the diameter of the part of the glass where the light travels, is typically either 62.5 microns or 50 microns. And this type of fiber is used extensively in the IT community, and a lot of it is already installed. However, for those of us in the Pro AV world and for broadcast use, it has very poor bandwidth because we tend to send signals that are not compressed, that are full bandwidth full bandwidth baseband signals, and we tend to send them in a simplex manner. That is, we just send them out from point A to point B with no return information as to whether or not it got there successfully. So we need as much bandwidth as we can in the fiber, and multi-mode fiber characteristics are poor for Pro AV and broadcast use, especially over the distances that we tend to use. A lot of IT professionals don't understand this because they see computer video being communicated, but it's a different type of video. It's compressed, it's packetized, there's an ACK-NAC protocol that it's couched within. So just keep this in mind. Now, inside of the multimode fiber, the light is very, very dispersed, and this adds to the distortion and decreases the usable bandwidth for a given distance. The advantage, however, to multimode fiber is that we can use relatively inexpensive VCSELs. The VCSEL is the electronic element that converts the electrical signals into light that come out of the transmitter and couple into the fiber. Now, with single mode fiber, its core size, as we saw before in the graphic, is much narrower. And this has typically in the 6 to 9 micron range. This type of fiber is used extensively in by telephone companies, cable TV operators, and of course in broadcasting as well. And it has virtually infinite bandwidth at almost any length, especially when you compare it to multimode fiber and for the types of signals and the types of applications that we use in professional video. Inside of the fiber, the light is very focused, okay, and this is what gives it its high bandwidth and low attenuation characteristics. It is actually less expensive than single mode fiber. If you can look at any catalog, compare the cost of single mode fiber to multimode fiber, any type of multimode fiber, for a given type of construction for a given distance, you will find that single mode fiber is actually less expensive. Now, this did not used to be the case, but around 10 years ago the crossover took place and single mode fiber is less expensive. The one drawback to single mode fiber is that you must use a laser in order to launch the light into the fiber. And the laser tends to be more expensive than VCSELs. So there's an added cost, if you will, to the transmitter box on one end compared to what you might use with multimode when you use a VCSEL. The advantage, and this is an advantage we're going to exploit in this webinar, is that it is easy to do what's called wave division multiplex. That is to add multiple channels of light onto one fiber. So comparing single mode and multi-mode fiber, the one thing I kind of ask all of you out there is that if you have a new installation, a permanent installation, where you're going to be installing fiber optic cable that's going to be buried behind walls, underneath a parking lot, inside of conduits, something where it's permanent, please use single mode fiber. I cannot tell you how many times we've sold product to customers for use with multi-mode fiber, only to come back a couple of years, a few years later, and say, well, now I'm graduating from this type of signal to something that requires more bandwidth, maybe composite video to SD-SDI, and I have all this multi-mode fiber that's run 3 kilometers. And we say, well, it doesn't have the bandwidth at 3 kilometers in order to support HD-SDI. If you had put in single mode fiber, you would be able to use that installation. So if the IT department in your installation is in charge of putting in the fiber for you, please double check what they actually install, because it'll probably be multi-mode fiber because that's what they're used to. And the bandwidth advantage of single mode fiber far outweighs any cost differences in the boxes that may result initially. Remember, bandwidth requirements will keep on increasing as time goes on.
John, we got a question. Is there a difference in distances that single mode or multi-mode fiber can travel?
Yeah, it's quite extensive. In fact, if you look at single mode fiber versus multi-mode fiber, for a given baseband signal, what you're going to find is that that relationship may be as high as 10 to 1. In some cases, it may be 20 to 1. The difference is that with single mode fiber, even if I get to the distance maximum, if you will, I have some techniques that are available or that to me to extend that distance. I can use higher power lasers. I can change the wavelength of the laser to extend the distance. With multi-mode fiber and with VCSELs, I don't necessarily have those tools, if you will, in my bag of tricks.
John, how does OM3 multi-mode fiber compare to single-mode fiber?
Well, I'm going to put that off for a moment
Okay.
because there's in a couple of slides we're going to see some differences.
Okay. Different kind of question here came in. Okay, it sounds like single mode is the way to go if you have a choice, but you don't always have a choice. What if you're running a facility where there's multi-mode fiber installed and you want to do some upgrades? What do you do then?
Well, if you want to add more signals, one of the things you can do is employ a technique called wave division multiplexing, where you can add two wavelengths onto that one multi-mode fiber, and that gives you some increased capacity. The other thing, if you want to increase the usable bandwidth, that is, you're trying to send a signal that requires more bandwidth, check with the manufacturer of the transmitter receiver products, because some of them will work with multi-mode fiber even though you may be limited in distance. But other than that, you may run out of rabbits to pull out of the hat.
Okay, thank you for that, John. Now that we've described the two different kinds of fiber, let's talk about the different variables for success.
Okay, so there are 4 variables for success. And when I say success, I'm talking about getting the signal that you want from point A to point B without errors or with an acceptable number of errors. That could be without glitches on the video or pops in the audio. The first is the bandwidth of the fiber. The more bandwidth we have in that fiber, let's say OM3 multi-mode compared to OM1 or single mode compared to multi-mode fiber, the more successful we're going to be. The length of the fiber cable comes into play. One of the problems with multi-mode fiber is that the longer you make the fiber cable, the more dispersion, the more distortion of that light that you get. And oftentimes what limits you to what the usable length of the fiber is for multimode is not the loss of light, not the attenuation, but the amount of dispersion or distortion that occurs of that light. So the length of the fiber cable comes into play. With single mode fiber, it's not a question of the dispersion as much as it is a question of the attenuation of the light, okay, as you increase the length of the fiber. The wavelength of the optical signal comes into play as far as success goes, because at 1550 nanometers we have less attenuation of the light than we do at, let's say, 1310 in single mode. So I can go a longer distance if I change the wavelength. It's one of the techniques that we can use. All right? And then finally, the data rate of the baseband signal. Today, even analog signals are converted to digital ones and zeros and sent serially over fiber. So what happens is that if I keep the first 3 variables the same, but I change the data rate, let's say I go from composite video to 3G SDI, and I increase the data rate of the signal, that's going to affect what usable length I end up having. Okay, I may decrease the usable length of the fiber, particularly with multimode. I may, for a given wavelength, as an example. So what happens is that the quality of the transmission is going to be a function of all of the above. Change one of these 4 variables, and it will impact the bit error rate and the usability from one end to the other. Okay, so these are the 4, think of them as 4 degrees of freedom where I can, that I have available to me. Now, getting back to the question about OM3 versus single mode. Here's a slide that I put together to give you an idea as to what the differences may be. On the left side, we have an axis called usable distance in kilometers, and on the x-axis, we have the data rate in megabits per second. Now, I put in three graphs for OM1, OM2, and OM3. And what you can see is that as I increase the data rate of the signal that I'm trying to transmit, my usable distance drops dramatically. So let's just take OM3, okay, that's this line here. As I go from, let's say, HD-SDI to 3G-SDI to 1080p HDMI, okay, my usable distance starts to drop. And you can see that if I just work with HD-SDI but change the fiber cable type back to OM1, and there's a lot of this installed out there, you can see that my usable distance may go from 1,200 meters down to maybe just a couple of hundred meters. So here, the dispersion in these types of multi-mode fiber, or the bandwidth that results, dramatically affects the usable distance for a given data rate. Now the question came up is, what about single-mode fiber? With single-mode fiber, quite honestly, first off, we'd be up off the graph, up here someplace, or even higher, because you'd have a usable distance on the order of probably 20, 30 kilometers, 40 kilometers, and the graph itself would more or less be a straight line, and then it would fall off dramatically. And then the fall off is as a result of exceeding the link budget, and we'll get into that in a moment. Okay, but the point is that with single mode fiber, you're going to be relatively independent of length until you run out of light, and then it drops off dramatically.
Okay, thank you for that, John. We have another question here. If we can go back to multi-mode versus single mode, the question is about connectors. Are there standard industry connectors for these kinds of fiber, or is it a free-for-all?
Well, there are different connector types. There's ST, LC, SC, FC. It's a real alphabet soup out there. And in each one of these types, there are specific connectors that are used for single mode versus multi-mode fiber. So you have to first settle on the type of connector that you want, and then settle on and then make sure that that type of connector is ordered to match the specific type of fiber that you're using. I will say that in Pro AV and broadcast, we tend to use ST connectors, that's Sam Thomas connectors. LC connectors are also used as it relates to the, I just want to advance this. LC connectors are used typically in rack installations because they give you more density. But we have found that most people preferred ST connectors. There are some SC, Sam Charlie connectors out there that are used, but again, we're finding ST to be about a 2-to-1 difference over LC.
Thank you for that, John, and keep those questions coming in. We'd love to answer them. So we've talked about success parameters. So let's move on to the next topic here. While fiber transport has far less signal degradation than other transport media, such as coaxial cable, there is still loss that needs to be factored in. This is referred to as the link budget, and John's going to talk about that next.
Okay, Josh. The link budget is sometimes called link loss, okay? And this is the maximum amount of attenuation or the loss of light between the transmitter and the receiver that can be tolerated. Fiber, any type of fiber, is not a perfect medium. Okay, just like coax or twisted pair, there's going to be loss of light that's proportional to the distance. So at some point, there's going to be so little light that the receiver can't detect it. And the amount that can be tolerated, the amount of attenuation that can be tolerated, is called the link budget. It's measured in dB. And just to give you some perspective, a 3 dB loss of light is a loss of half of the light power, or the brightness, if you will, that's been lost in that fiber optic link. Now, the maximum loss that can be tolerated, or the link budget that can be tolerated between the transmitter and the receiver, is going to be specified by the product manufacturer. Make sure that they specify it. Sometimes they'll specify just the distance. They'll say, oh, this will work over X number of meters or kilometers. That's only half the story, because you can have a tremendous amount of loss in a simple link and you will not achieve the distance, okay, because of other things. You may say, hey, the manufacturer said this will go 500 meters, I'm only going 400 meters, and it doesn't work. Well, it may be because you've exceeded the link budget. And if you don't know what the link budget is, ask the manufacturer. Okay, so to illustrate this, very simple. Over here, let's say we have a transmitter who specifies a launch power of minus 3 dBm. Okay, this is the absolute power of the light that is launched at the transmitter. Okay, now the receiver spec should give you two numbers. One is what's called the saturation point. That is, what's the maximum brightness of light that can be tolerated by the receiver. If the light is too bright, okay, then what's going to happen is that the photodetector on the receiver will saturate and it won't work. At the same time, the receiver has a minimum sensitivity. That is, what is the minimum amount of light that the receiver can tolerate. So the link budget is going to be the difference between the launch power and the receiver sensitivity, and in this case we have a link budget of 17 dB.
Wow. All right. Thanks, John. Now that we've covered the basics, let's have some fun. Using the information that we have covered, we're going to describe the different ways that video and data signals can be simultaneously transported or multiplexed over a single strand of fiber. John?
Okay, let's look at the traditional way that people have thought about fiber optic communications for video and audio. Okay, a very simple, as I like to call it, the optical extension cord philosophy. We have a fiber optic transmitter that takes in an electrical baseband signal, let's say it's 3G SDI, and magically inside of that box it gets converted to an optical signal at a wavelength of 1310. Okay, we then take the output of that transmitter and we put it out over one fiber optic cable, one core, one piece of glass, and we send it over to the receiver, where magically that optical signal is received and converted back into an electrical 3G SDI signal. Very simple concept. Okay, well, we can modify that traditional thinking in two very important ways. The first is that we can electrically multiplex these baseband signals. That is, inside of that transmitter box, we can combine multiple baseband signals, and they can be of different types. We can electrically multiplex them and then impose them onto one wavelength. Let's say in this case it's 1310 nanometers. Okay, so we have in this case 1, 2, 3, 4 different electrical signals that we've electrically multiplexed together by digital techniques and taken that data stream and putting it out onto one 1310 nanometer signal. So this is electrical multiplexing. All right. Now, the second technique that we can do is what we call optical multiplexing. Here what we do is we combine multiple optical signals, either internal to the box or external to the box, onto one signal. So here is the same transmitter that we had before, right, with our 3G SDI and our 2 analog audio and our contact closures that became impressed on to one 1310 nanometer wavelength. And then we have a second box, and this now is taking 10 composite video signals, doing an analog to digital conversion on those signals, and then digitally serializing them through the magic of technology, and putting that on a different wavelength, in this case 1550 nanometers. Okay, now the 1550 nanometers now gets combined optically with the 1310 and placed onto the WDM. And the WDM is just a passive device. Okay, there's nothing electrical about it. It's just a 3-port device. There's a 1310 leg, a 1550 leg, and a common. And what it does is it optically combines the 2 wavelengths onto a common fiber. Okay? So this is optically multiplexing. Now, we can expand this using a technique called wave division multiplexing. And this is a method for combining multiple optical wavelengths onto one fiber. And this is very similar to the way RF channels are multiplexed onto one piece of coax in the world of cable TV, except we're using light instead of electrical signals. And what this does is it increases the communications capacity of that one fiber because we're able to use more light. And this technique is typically used with single mode fiber, but it can be used with multi-mode fiber, although it is more expensive and the techniques are proprietary. Even if you're going to optically multiplex just 2 wavelengths, it is more expensive to do it on the multiplexer itself. The WDM itself is more expensive for multi-mode than it is for single mode fiber. This is another reason to use single mode fiber. You can also use this for bidirectional signaling. In our illustration before, we showed all of the signals going from point A to point B. But in fact, you can have the signals going, one signal, one wavelength from point A to point B, and the other one from B to A. And each wavelength, as we saw, can carry 1 or more baseband signals. So this is a tremendous capability that just a simple, single, inexpensive strand of single-mode fiber has. Okay, now there are 3 different basic types of wave division multiplexing. Okay, we have what we call simple, coarse, and dense. And the uses for this are when, there's a couple of reasons why you would want to do this. One is when you have a limited number of fiber cores. Maybe you have fiber that was installed between buildings on a campus many years ago, and now you want to add more signals to it, but it's prohibitive in cost to run more fiber. So you want to be able to expand the capacity, if you will, of each one of those fibers. Another reason for it is if you have very long distances, to save on the cost of the fiber and the installation costs associated with it. Maybe you're going from one city to another. Maybe you're going under the water from one island to another or one continent to the other. Okay, so you put more money into the transmission and the receiving end, but you save on the cost of the fiber installation. Some typical scenarios for this are studio to transmitter links, college campus media center to a stadium to get the sporting event back to that media stadium, truck-to-truck signaling in a OB environment. This happens a lot in golf matches. And one of the more recent applications is to take 4 3G SDI signals, let's say from a camera, for 4K UHD transmission, to take those 4 3G SDI signals and optically multiplex them for use of a one single core fiber. Okay, so let's look at simple wave division multiplexing. Here we are using just 2 wavelengths that are optically combined onto the same fiber. Now each wavelength can carry 1 or more baseband signals, as we saw. I want to keep driving this home because a lot of people think that there can only be 1 baseband signal per wavelength when you do multiplexing, and that's not the case. If we are using single mode fiber, we typically use 1310 nanometers and 1550 nanometers as the wavelengths. If we're using multimode fiber, we typically use 850 nanometers and 1310 as the 2 wavelengths. And both signals can be either in the same direction, or you can use them bidirectionally, one wavelength going in one direction and the other going in the opposite direction. Okay? So let's look at a simple example, and this is using internal simple wave division multiplexing. Okay. Now we have a camera with an SDI output, and at the same time we have a laptop with Ethernet, and we have RS-422 type data for PTZ or control of the camera. All of these signals can not only be digitally multiplexed, but also optically multiplexed depending upon the types of signal that are being communicated. And in this case, the signals are going over one single mode fiber in a tactical fiber bundle as an example. We're using just one of the cores to transmit that. And then at the receive end, it's being broken out to an SDI monitor or production switcher. The Ethernet may be connected to a server, and then we have the controller for the PTZ control of the camera. So you can see that by using a combination of digital and internally wave division multiplexing, we can send this over one fiber. This is just one example, and it's just one way of illustrating a simple WDM scenario. Now, another technique is called coarse wave division multiplexing, or what we call CWDM. And this is a technique for placing up to 16, typically 16, sometimes 18, different wavelengths onto one fiber. Now the wavelengths that are used are typically 1510, 1530, 1550. The important thing is that they're spaced 20 nanometers apart, and there's an industry standard as to what the wavelengths actually are. And it is possible to do this in the 850 nanometer band for multi-mode fiber, but this very rarely occurs. And however, it is used with what we call HDMI or DVI fiber optic dongles, except that it's done on a proprietary basis, and there's no standard as to actually what specific wavelengths are used. Now, this technique can be used for bidirectional transmission as well. We can have 3 signals going one way, 5 going the other. There's all sorts of possibilities. And the beauty of this is that you can change the direction as your operational needs change from day to day, week to week, year to year. Okay? Because the CWDM glass, the multiplexer itself, doesn't care about the direction. Okay, so let's look at a simple example. This is, again, just wanted to add, this is also very useful for what we call drop and repeat topologies. Okay, so a basic 4-channel system. On the left side we have 4 wavelengths that are coming from 4 separate transmitters. Okay, these could be baseband transmitters that are on different wavelengths. They go into a CWDM, which is a 5-port device. There's 4 optical pigtails that come out of it that are tuned, if you will, or filtered for the specific wavelengths, and then a common, which goes into the one single mode fiber. And the same type of device is used at the other end that would then separate out the 4 different wavelengths. We can also do this on a bidirectional basis, where one of the wavelengths will be in the opposite direction, while 3 are in the original direction as well.
Thank you for that, John. We have a few questions that came in about multiplexing. First one says, you mentioned bidirectional. Is that full duplex or half duplex?
Full duplex. The channels are totally independent of each other. So you can be sending SDI from point A to point B at the same time you're sending 16 channels of audio from B to A. It's full duplex. They're totally independent.
Okay. We have another question that asks, can you multiplex 850 with 1310?
You can in a simple WDM. Yes, you can, but it's typically only used with multi-mode fiber, not single mode.
Okay, great. Okay, let's see. Now that we've seen the different kinds of multiplexing, let's look at some actual systems where these are being deployed. In actual application, these systems can get very involved and can transport a wide variety of varied signals through a facility. John's going to walk you through a few examples But please, if you have questions specific to your own situation, we'd like to hear them. We'd like to hear from you about them. Thank you. John?
Okay, so let's go back to the basic two-way CWDM system, and we're going to build on this. You'll see how. Okay, so the first thing, and if you hear my mouse click, pardon me, because I have to do that for the pointing. We have an SDI signal over here going into an SDI transmitter. The important thing is that that transmitter is outputting on 1530 in this example instead of the normal 1310 wavelength. And that's going into a 4-port CWDM, again over that one fiber, okay, which then gets recovered on the other side, on the B side, and recovered the baseband signal. But the B side is also originating an SDI signal on a different wavelength, in this case 1510. And then that signal gets recovered on the A side. All right. Now the important thing to note by doing this with a 4-channel CWDM is that we have 2 spare ports. And we have a lot of customers that do this because they want that expansion capability. What these ports will do in the future, who knows? Maybe they'll be used for 4K, maybe they'll be used for audio, they can be used for anything. And they can be used without upsetting the original use. Okay? So these are all independent of each other. All right? Now we can take that same concept, expand it to an 8-channel system, okay, where we have 8 CWDM channels, and we're going to use 6 of them. And the 6 of them are 1470, 1490, 1510, 1530, 1550, and 1570. Notice how they're spaced 20 nanometers apart, as I mentioned before. And by using 6 of them, we still have 2 spares. Now, typically, CWDM devices are available in 4 channels, 8 channels, and 16 channels. Okay, so keep that in mind. But here, we're showing the bidirectionality of it. We have an SDI transmitter at 1470 that's being recovered at the far end. But that B end, the far end, is also sourcing an SDI from a transmitter that's also embedding AES audio, putting it on a different wavelength to be recovered on the far end. All right? Combined on this system is another transmitter on a different wavelength, but it's transmitting 3 channels of composite video and stereo audio, and that's being recovered. What's interesting about this mix, this 6-channel system, is that the signals do not have to be the same. And we've combined digital multiplexing, like over here on the 7820, 3 channels of video with 2 channels of audio, along with optical multiplexing, to achieve a system on just one fiber that has a mix of all different types of baseband signals in a bidirectional manner. Okay, very, very powerful. So you may have had an installation where you had just one composite video and stereo audio that was installed 10 years ago using one fiber, and now you want to expand it. Well, look at all the things you can do now on that one fiber, and this is just with an 8-channel CWDM. Okay, let's expand on this. This is a more complex system, okay, and this system, what we're doing here is we have a 2-way optically split CWDM matrix system. Now here what we're doing is we're interposing an optical matrix that has 8 ports, 8 optical inputs. Okay? Inside the matrix is digital switching, and we have 4 optical outputs on 4 different wavelengths. These 4 outputs go into an 8-channel CWDM, and the common of that CWDM is going to go through a 1x2 splitter. And this 1x2 splitter is a passive device. It's very similar to the cable TV 1x2 splitter you have in your home to take the cable TV drop and drive 2 separate set-top boxes. The exact same concept exists in the world of optical communications. except we do it optically instead of electrically. Now, what this is showing is that we have a main studio and we have a remote Studio B and a remote Studio C. And what we're going to do is we're going to take these different sources and be able to route them to any one of the remote studios by going through the matrix first, then through the CWDM, then through the splitter, and each leg of the splitter goes to a CWDM at Remote Studio B and Remote Studio C. But you'll notice that these remote studios are also sourcing either audio or composite video or maybe their own SDI with embedded audio, and they're sending it back on a different wavelength through the same CWDM, through the same splitter, back through the same CWDM at the central equipment location, and those four sources from Studio B and Studio C appear as inputs to the optical matrix. Okay, so we can route signals between the studios themselves as well as from the main studio to either one of the remotes. Okay, I've created slides that are even more complex than this. Okay, but we don't have the time to go through it. But if any of you were fortunate to be at one of my seminars where I spend a lot of time on this, you know that these can get very complex. The important thing to note is that this fiber optic cable or core between the two outputs of the splitters and the two remote locations is just one single mode fiber core. This is not a bundle. It has to be no more than a simple single core.
Okay, John, we have a few questions that have come in here. One is, we're talking about adding two-way communication onto fiber. We're talking about putting more signals down a single fiber core. Does doing these things limit the distance that the signals will travel?
No. You will get this for the same optical components that are used. You will get the same distances. You'll get a little bit of what we call insertion loss. The CWDMs will introduce a fraction of a dB of loss on each end, maybe as much as a dB depending upon how they're designed. So as a practical matter, you won't limit your distance, because one of the things that you do when you use a CWDM is you tend to use longer wavelengths, and that will result by themselves in increasing the length, because there'll be less attenuation in the fiber as you go up in wavelength compared to if you just use 1310. So it's kind of a trade-off. On one case, you're using wavelengths at longer wavelengths, lasers at longer wavelengths, which increase the distance, but you're cutting down on, you're introducing a little bit of attenuation on each end as a result of the CWDM. So it's kind of a push.
Okay. I have another question that came in. We're talking about a lot of different, adding transmitters and receivers here and there. Would it just be cheaper to encode to a multiplexed ASI stream instead of doing all this?
You can certainly do that. The difference is that you no longer have a baseband signal, because you've encoded it, you've compressed it, and if you're trying to preserve the baseband signal, you lose that when you decode it back. So these systems are designed to preserve baseband signal integrity. Some people may say, well, why don't I just encode it into H.265 or 264 or MPEG-4, something like that? And yes, you can do that. And the problem is that you no longer have a lossless signal unless you have a very small amount of compression that takes place. Okay. Also, it becomes more difficult to mix multiple or different types of baseband signals, contact closure, different types of audio, different types of data, Ethernet, in those types of encoding schemes.
Okay, we have another question that came in. We were talking about doing point-to-point. Can we do point to multi-point?
Yes, absolutely. Couple ways to do it, and you're seeing it here. Let me go back to this. This one, but the simplest way to do it is with a splitter. Okay, you have a 1x2 splitter, so you have a point to 2 points. Okay, they also make a 1x4 splitter. The problem with passive splitters is when you do that, you introduce about 4 dB of loss in each leg. So you go back to that link budget that we showed before. Remember, in that example, we had a 17 dB margin. Well, now by using a 1x2 passive splitter, I've already introduced 4 dB of loss in that link. Now, there are what we call optical distribution amplifiers, which are active devices where there is no loss. And there you can cascade them. We've had customers that have gone up to about 12 or 15 different points from a single point. Okay, they act as just very wide distribution amplifiers to go from point to many, many multi-points, but without introducing any loss because they're active. So yes, that's very, very common actually.
Okay, John, we have another question for you. What is the typical amount of latency of baseband signals when transmitted over fiber?
Good question. We get this all the time. First off, the propagation of light in the fiber itself is approximately equal to the propagation of electrical signals in coax, okay, which is roughly, and it depends on the fiber, it's roughly 2/3 the velocity of light. So my rule of thumb is about, now I've got to remember this, it's about 5 nanoseconds per kilometer, is that right? Or 5 nanoseconds per meter. I'm sorry. It's about 5 nanoseconds per meter. So there's no latency, no appreciable latency there. As far as the boxes themselves go, one of the reasons why you keep it as a baseband signal as opposed to the compression is to eliminate any latency that the box itself would introduce. Okay, so because there's no frame buffering, because there's no compression and decompression, no encoding and decoding, the latency through the box itself is typically measured in nanoseconds, 70, 80, 90, 100 nanoseconds on each end. So you add that, the transmitter latency plus the receiver latency plus the latency in the fiber, which is a function of distance. So overall, it's no worse than it would be through an electrical coaxial-based system.
Great, thank you, John. And we only have a few minutes left of the webinar, so I'd encourage you to get questions in if you've got them. We have another question here. What would be the typical configuration for a long-distance fiber haul, say, between two different cities?
Well, again, it depends on what baseband signals and how many baseband signals. But typically, certainly single-mode fiber would be used. You would use a higher wavelength, such as 1550 nanometers, because for a given fiber, and a given launch power, you'll be able to go a longer distance because there's less attenuation in the fiber at 1550 compared to 1310. If you still need more distance, you can use ask the manufacturer to put in a higher powered laser. Typically the launch power is maybe -3 dBm, but you can get simple lasers with a higher launch power of maybe +6. So you'll add about 9 dB to your link budget. And again, it depends on the specific number and types of signals, but those are typically the two techniques that are used for the much longer distances.
Okay, we have another question. Could you describe
I'm sorry. Let me add one other thing. There's a third technique.
Okay.
And if that doesn't work, you can put in what we call a 1-to-1 ODA. That is an active optical distribution amplifier where the input comes in, it gets regenerated, reclocked, and then relaunched on a new laser, so that you're basically reestablishing the power, and you would put that at some intermediate point. Okay, there's one other, before we go on to the next question, there's just one other thing I wanted to mention, and that had to do with dense wave division multiplexing. This is another technique where you can put up to 160 channels in the 1500 nanometer band. Okay, instead of it being 16, you can put 10 times as many. Now the channel spacing is less than 1 nanometer, and the result is that you need very expensive lasers that must be used to maintain the channel spacing. The result is that there are only a few applications in broadcast where this is used. It's mostly used for internet backbones where you have a large amount of information to be communicated, and transoceanic and intercity communications.
Oh, okay. One last question here. Could you describe the advantages or disadvantages in using a dual fiber versus a single fiber?
Okay, well, certainly the advantage with dual fiber is that you've doubled the capacity of your link, and if that's available to you, you can cut back or may not need any wave division multiplexing because you have the 2 fibers available. The disadvantage is that 2 fibers cost more than 1 fiber. And it may be that you have a tactical cable where the 2 fibers are there anyway, in which case there's no incremental cost, which is fine. Then I would advise you to take advantage of those 2 fibers to the extent that it lowers your costs at the transmission and the receiving end. Some people, even though they have the 2 fibers, they won't use the second fiber. They keep it as a spare. So that would be it as well. Okay, so to summarize, I want you to think differently when it comes to your fiber optic designs. Okay, start with a clean sheet of paper and use fiber from the start, and don't just think of it as an optical extension cord to solve a copper distance problem. Okay, aggregate your baseband signals and your wavelengths. Take advantage of the properties that are unique to fiber. And if it's your first time working with fiber, start small to gain confidence with it. And design your systems to take advantage of the unique attributes that fiber has over copper. And always, if possible, use single mode fiber. I can't overemphasize this point. Josh?
And that concludes our webinar for today. I'd like to thank John Lopinto for sharing all his technical wisdom with our audience today. Also, I'd like to thank our sponsors, Campflex and Communications Specialties. And there will be, in about a week, a version of this webinar will be posted on the Communications Specialties website.
That's comspecial.com.
Comspecial.com. Thank you.
Thanks, everyone. We really appreciate it. At the end of this, there'll be a questionnaire that we'd just like to get some feedback from you on what you thought about the seminar.